Alright, chemists, so we're about to look at the atmosphere. We're moving on from how to detect certain chemicals, and we're now going to look at how we monitor what's going on in the environment. So today we're going to look at one, describing what the atmosphere is made of. We've seen that before. We're also going to look at what are the main pollutants in the lower atmosphere or the troposphere, as well as we're going to be able to describe the different roles that ozone has in both the troposphere and the stratosphere. So here we see the layered nature of the atmosphere, and what is really the defining feature is the way the temperature changes, which we'll get to in a minute. So the atmosphere essentially is a gaseous mixture surrounding the Earth. It's held in by gravity. The dry atmosphere is composed of the following gases. This is all a bit of revision. So we've got nitrogen at 78%, oxygen at 21. You need to know it to these levels at the moment. Argon at 0.93 or 1. Um, carbon dioxide at 0.036, and the 0.004% of it is the other stuff, which we'll have a look at in a minute. So that's, by the way, that's the makeup. That's the remainder right there. So 0.4% of it, we'll see what that is in a minute. So the dry atmospheric composition varies little with altitude. That's really interesting. So as we go higher, right up to about there, the composition doesn't change. The amount of stuff will, but the composition doesn't change. This is by volume as well, not by mass. Um, so carbon dioxide is increasing. It has done over the last 150 years, and this is largely due to things we're doing to it. So the water vapor there does change. Now, it varies by a factor of 10 in the troposphere, but between the troposphere and the thermosphere, it also varies quite a lot. So the atmosphere consists of a series of layers, and basically what defines these different layers, and they're very, very sharp, is the way the temperature moves as you go up. And we'll have a look at what that is in a second. Alright, so first off, here is your pie graph. We've all seen it before. The remaining 4% is this here, okay? So 0.037, they've got it here. It's 0.036 will run for the moment, is carbon dioxide. That shouldn't say that. That and that should be swapped around. Then you've got neon, helium, methane, krypton, and hydrogen. So let's have a look at the layers. The troposphere, which is Earth's surface and like about 15 k's up, temperature decreases as you go up. Then you hit the stratosphere, temperature increases as you go up. This is why you see that graph where it's like temperature, altitude, temperature, and it does this. It starts over here and it moves like that. That's because what the boundary of each layer is where the temperature starts to turn direction. So here the temperature increases. When the temperature starts to decrease again, we call that the mesosphere, because as you go higher there, the temperature decreases. Then you hit the thermosphere, which the temperature goes up as you get higher, and then we hit the exosphere, which is where you're starting to enter space. The ionosphere incorporates these two zones, and that's where radiation is creating ions in the air, and that's also where your auroras tend to exist. So if we have a quick look here, by the way, the stratosphere about 25 kilometers up, we'll see this in a few minutes, is where the ozone layer tends to live. So what are the pollutants that we have to deal with? Well, first off, a pollutant is something that has a deleterious or negative effect, harmful effect on the natural environment, and there's a lot of them. And they tend to come from combustion of fuels, smelting of metals, and solvents that we're using. So let's have a quick look at what they are. Carbon monoxide is from the incomplete combustion of fuels. SOx, so all the sulfur oxides, tend to come from both sulfur ores and combustion of fuels. Again, NOx, so SOx and NOx, or the nitrous oxides, they're all combustion of fuels at high temperatures. With hydrocarbons, okay, they tend to come from unburnt fuels as well as solvents. Particulates, so this is again the carbon soot, and like mining operations where you're moving a ton of earth, you see a lot of dust in the air from that. That causes real problems. Lead petrol, less of an issue, but still a very serious issue throughout the world. Lead smelting still needs to happen. Renovations of house with lead paint. We don't use lead in paint anymore, but it's still something that's coming up and being a real issue. And then we've got ozone. Ozone is really interesting. Ozone comes from an interaction between sunlight, hydrocarbons, and nitrogen oxides. And in the upper atmosphere, it's wonderful. But in the lower atmosphere, super bad. Let's have a look at what is. Oh, hydrocarbons. They all tend to be carcinogens. So, that's something worth avoiding. All right. SOx and NOx will start there first. Okay, the first thing, it leads to acidified rain. We're not going to go over that again in much detail at all. But nitrogen dioxide, when it mixes with HV, which is high energy ultraviolet light, we'll get into this in a bit more detail later on, gives you an oxygen free radical. So this is an oxygen that is an ion, and it's a free radical. That free radical mixes with other oxygens. Okay, free radicals are something we've covered in the past, so hopefully if you're not sure, look that up again. That free radical joins with oxygen, the gas, and it creates ozone. So that joins up. Now, so NOx adds to ozone in the lower atmosphere. Volatile hydrocarbons. So the carcinogens, that's cool, but ultraviolet radiation, so that's the HV, plus nitrogen oxide, plus volatile organic compounds, also give us more ozone. Okay, and it's actually one of the big aspects of all smog, and we can see it here. For example, here we see the time of day. All right, so there's our nitrogen oxide's been pumped into the atmosphere. It hits midday when the energy's at its highest. The ultraviolet energy is at its highest, and that's when ozone production starts to really ramp up. Okay, and you see that as this gets used up, it shrinks down, ozone gets up, and that's our dramas. Carbon monoxide. So carbon monoxide poisoning works like this. So your hemoglobin carries your oxygen. Cool, we know this, and it carries it inside. A molecule of carbon dioxide can chill in there as well. Carbon monoxide instead, though, gets in, and it binds really tightly. The oxygen and the carbon dioxide can no longer bind into the hemoglobin. So carbon dioxide is carried out. Okay, that's what the hemoglobin is used for, is carrying out carbon dioxide and carrying oxygen in. The carbon monoxide gets in, binds up with it, and it causes suffocation because we can't get rid of the carbon dioxide in our blood. So that's what actually kills us, is the carbon monoxide binds up to our blood and stops us being able to get the carbon dioxide out of our system. Ozone. Ozone has these problems here. One, it's a greenhouse gas, okay? And down low, it causes real problems. Toxic to plant health, toxic to human health. But if you're toxic to plant health, you're going to increase the warming as well, for obvious reasons. So here's our ozone. It comes down, it increases global warming, does crop damage, reacts here to make more ozone. That's called photochemistry because it uses the light from the sun. So let's look specifically now at ozone. Alright, so ozone's found at very low levels in the atmosphere and at very low levels in the lower atmosphere, about 0.02 parts per million in clean air. So it tends to be formed through sunlight, hydrocarbons, and nitrogen oxides acting together, so NOx, hydrocarbons, and sunlight. And this gives us higher concentrations in the troposphere, so it increases it. And this is why it's a big issue in the city, where you've got a lot of that stuff pumped into the air. And we've also seen previously that's why it's an afternoon pollutant, which is kind of cool. All right, so it's poisonous to humans, as well as plants and animals, etc. It's really useful for sterilizing, and it's pumped through water treatment to sterilize water, which we'll get to later on. With its effects, in large normal concentrations, including, but not limited to, breathing problems or respiratory problems, same thing, headaches, fatigue, and death if it's in high enough concentrations. This is what it looks like. So we've got the bent structure there, which means that hang on a sec. Sorry about that. What that means is we have a polar molecule. This bond is not polar, this bond is not polar, but the shape of it gives an uneven distribution, and we have a polar molecule. And this end here is the positive end, and these ends are negative. Alright, so that's obviously not worked super well either. Now, the roles of ozone. So we're continuing on. Basically, in the Alright, so upper atmosphere ozone is what we're talking about now. So ozone exists at higher levels in the upper atmosphere and the stratosphere, going from 2 parts per million to about 8. And this is where 90% of the atmosphere's oxygen is found anyway, is locked up in ozone. So, that should say ozone, not oxygen. That should say ozone. So in the upper atmosphere, both oxygen gas and ozone absorb different parts of the ultraviolet spectrum. Um, and it creates a cycle, which we'll see here. So, oxygen absorbs high energy ultraviolet radiation as part of the ozone formation process. So we go oxygen here, it absorbs high energy ultraviolet radiation. Okay, this gives us 2 oxygen free radicals. The oxygen free radical then joins up with another oxygen, and here we have ozone. Ozone absorbs medium energy, so medium energy ultraviolet radiation, and this is what decomposes it. So it's this one here which tends to cause skin cancers. It's this one here which tends to be most deadly to life in general. So this is why ozone is super important to life in the upper atmosphere. So here we have high energy HV ultraviolet radiation creates ozone. Okay, medium energy ultraviolet radiation destroys ozone, and you can see that the process is somewhat cyclical. So here we go. So oxygen is breaking apart. So ozone's breaking apart to give us this. So here we have the ozone plus another oxygen, so plus another free radical here gives us 2 oxygen molecules. Now, the second step in these reactions tends to be exothermic, which is why ozone contributes to global warming. So this is why it increases the temperature in the stratosphere. The stratosphere, as you'll notice, as it goes up, increases in temperature. So the ozone layer acts as a radiation shield in the upper atmosphere, absorbing both of these forms of energy. And that's really important. We need that to happen. And here's just a quick breakdown of where it is. So here we see low levels of ozone. Up here we've got most of it, and about 90% of it exists in this section right here. So here it's beneficial, and down here it's harmful. Alright, it's a long one, and we'll see you in class. Thanks for hanging in.